why don't we go to Mr. Michael Perrone, second law of thermodynamics. And Michael is actually working on, he's been working with Daniel Sheehan on a few projects related to this, some thermal battery projects. But I think he was going to start us out with kind of some overview info. So Michael.
So yeah, so I can, unfortunately, I was still working on the presentation for this. So, but what I can do, I guess, is talk about at least in general, yeah, I could talk about like what I've got going on in general terms and
yeah, go for it.
Non-informal sense, and then if and actually, then when I finish this presentation, we can go over the formal presentation on your channel afterwards and get all the details up.
Okay, well, why don't we do that then? Why don't we, if it's okay, just give everybody a rundown on,
sure,
because you've been working with Professor Sheehan, and then you've been continuing to do research, and then you're planning projects also. So if you could maybe just do an overview of all that, that'd be great.
Sounds good. So, I guess I'll use what I have in my presentation as an outline while I talk. So, where to begin? So what, I talked to a friend of mine long ago, and he was saying at some point, if the laws of thermodynamics hold, we're going to have to try to escape this universe to escape the heat death of the universe. And I thought to myself, well, what if we're trapped not by the laws of the universe, but by our understanding of them? If there's any chance that the laws of thermodynamics are, as we understand them, are not the true laws of the universe, then that would be just as effective as trying to escape a universe, as trying to redefine our understanding of it. And once I dug into the info or the research, I saw that especially recently, there were a number of counterexamples to the second law of thermodynamics, with experimental replications in multiple labs and based on actionable theories and principles. So what I would like to do is kind of give an overview of like, well, the intention of this presentation was to give an overview of that, but some of these things I still haven't added any of the pictures. So we'll just go as, yeah. So anyway, where to begin here? As a background knowledge for this, you really want to know, as a college or graduate student, you got to know your linear algebra, your calculus, and your statistics as a starting place. Then from linear algebra, you can learn Markov chains and Hamiltonians and Lagrangians. From calculus, you learn your PDEs. From statistics and PDEs, you take a look at quantum mechanics, and then the Hamiltonians and Lagrangians come in there. And yeah, there's a ton of different things to learn in order to really formally approach and formally test thermodynamics. You need to be aware of all of this stuff in order to really formulate and test these things. So, I'll go over that with Tim at a later date, I guess. So I guess the weak point for the second law of thermodynamics at the moment is it's not in the formula. So thermodynamics itself is self-consistent, but the issue arises or the potential violations arise from what axioms and assumptions that we make. So if I can jump to that. So for example, we assume something called ergodicity. Ergodicity is basically that every possible state of your system is accessible, which means that the individual microstates all have similar order of magnitudes of probabilities of being reached by other microstates. And under that assumption, if you flip a coin for where the energy heads to in the next instant of time, then eventually the energy will spread out and disperse. And maybe the probabilities aren't equal everywhere, so you'll get some Hamiltonian, but it's still a steady state ultimately. You have some function that the system settles into as a minimum, as a steady state. So and then you can do no further work and entropy is essentially maximized. So that's an assumption and it can be violated. There are a number of physical counterexamples like the graphene energy harvester. So in those sorts of situations, you have a state like thermal phonons in a lattice, and it gets captured into a capacitor. And then the probability that that energy will randomly go back into thermal motions in the material from that capacitor is negligible. The capacitor can hold charge for centuries or whatever. So that violates ergodicity. There's a lot of examples like that. So for the thermodynamic limit, that's another assumption. Basically, we're assuming we have enough particles to work with that statistical averages work, or well, all statistics works. You need sufficient particles that you get, for example, a Boltzmann distribution, or just a normal distribution if you're working in the abstract case. And if you have just like 10 particles, temperature is not well defined. So every once in a while, these 10 particles will move around and maybe they'll all go in the same direction. What's the difference between 10 particles moving in the same direction and something that's really cold that's just what's the difference between the temperature and the motion in that situation? Temperature becomes poorly defined. And actually that's how people make Bose-Einstein condensates. If you have a laser, you can make sure that all these particles are moving up and down at the same speed. And yes, the particles collectively have a lot of kinetic energy, but relative to each other, they're moving very slowly. So relative to each other, they're very cold. That's the idea there. And when you have poorly defined temperature, then you also have your other thermodynamic variables poorly defined. And that can be exploited. And there's a couple of examples of that later on. And then Louisville's theorem is very important in equilibrium thermodynamics. But it really only holds for closed ergodic systems. You can have situations, you can have open systems where your volume in phase space changes. And that's anyway, yeah, all of these things don't necessarily hold. You have to make a lot of assumptions about your system in order for them to hold. And then from those assumptions, the rest of thermodynamics follows. And the rest of thermodynamics is self-consistent mostly. There's a few little things here and there, but really these assumptions themselves are not necessarily true for every physical system. Moreover, it's important how you define your boundaries for your system. So I got one of these pictures here. Yeah, so this will do for now. So get my camera. Yeah, so if you have a closed system, you can have Poincare cycles where energy moves around, and that doesn't do any work unless you define your system such that there's a heat sink and the system of interest. So if there's two things interacting, then you can define like thermodynamically, work is not defined unless you have at least those two things interacting with each other. So that's, yeah, how you define your thermodynamic variables depends on where you put your boundary conditions. So you can have a system that for all intents and purposes is doing something that looks like work. And then just because you say, oh, this is one system and that's another system, it doesn't count, at least logically, as work, unless you change your definitions of which is what counts as your system. So for the simplest possible example, to get the core idea of where these potential violations arise, we can use Markov chains. There's one thing here, and where's the other one? Yeah, so for Markov chain, so Markov chains are in some sense analogous to, where's that thing there? Just making sure. Okay, yeah, it's working. So Markov chains are in some sense working, in some sense, this is a state vector. So you have some energy in some states, and that's your microcanonical ensemble. And you have some probabilities that the energy goes from one state to another state in your system. And the important thing about Markov chains is that, at least multiplying on this side, all of the rows add up to 1. That's not necessarily true for columns. So that it's a simple matrix multiplication, but what it gets you when the rows add to 1 is that the quantity in that vector is conserved. So there's 2 examples in Markov chains which are not ergodic. And those are the absorbing Markov chain and the oscillating Markov chain. This is the simplest possible example for the oscillating Markov chain. And generally speaking, it doesn't have to be that simple. But generally speaking, the antisymmetric terms are the ones that are important for the oscillations. And then for absorbing Markov chains, you have one state where energy can enter that state via the column here, but it can't leave that state via the row. So you can think of that as you multiply your state vector, eventually your Hamiltonian will become essentially a Dirac delta. All of your energy will go into that state. And then nothing will happen, no work will be done if it's a closed system. Now with the oscillating Markov chain, you can do something interesting. You can, if you choose this to be half of that to be your, well, essentially the oscillating Markov chain minimizes the Poincare recurrence time. So that is, I guess, a conjecture at this point, but I think I can probably find a mathematical proof for that. But what's interesting is the Poincare recurrence time, if you know what state a system will be in after a certain amount of time, then you can take advantage of that. So if you split the system, like you set up your boundaries like this, then all of your energy goes to, all of your energy goes to one side due to how you set up your transition probabilities, and it goes to one side in a predictable amount of time, then you can use that to do work in the other system. So that's kind of the simplest possible example. So Markov chains are kind of an extremely simple way of thinking about these sorts of systems. They're ultimately, you want your model to be based off of elementary quantum mechanics, and that you basically use Louisville's equation with the density matrix and all of those things. And there are a whole bunch of more thorough models like the Redfield equations, Alverdian-Neuwensen theorem. That's a simple model as well, I believe. And then there's the fish trap model and the sewing machine model, which are from this book, Challenges to the Second Law of Thermodynamics. So that's a good place to start. And yeah, those models, the fish trap model is kind of self-explanatory. You build a quantum system such that when a particle reaches a certain interface, it passes through. Not if, but when. So it's a stronger statement slightly than Maxwell's demon. And the only way that can be done is with quantum correlations from the polarons around your materials. So you would have to have some sort of enzymes or something along those lines that can interact in such a way that when they come into contact, they undergo this process. And then the sewing machine model is cool. It's basically you have whatever micromolecules that dissociate in an aqueous environment. Then you have an enzyme which brings them back together. And if there's a small dissociation energy associated with them coming apart, then that enzyme will recover a small amount of energy from doing that process. And one of the questions with these sorts of systems is, if you can simply recycle ambient heat, then why don't we see it in nature? So I have two thoughts on that. One, the energy density could be so much lower that it's not competitive with systems that use chemical energy directly, because you're talking about thermal interactions, which are in general, the volumetric energy density is 1,000 times lower roughly than a direct chemical reaction, of that order of magnitude at least. And then the other concern is the amount of resources that it takes to create an enzyme until that enzyme breaks. It can't recover the correct amount of energy to make that sustainable under those circumstances, or resources or whatever. And that's possible perhaps. Or maybe it's difficult in biology for some topological reason, sort of like how wheels, we were perfectly able to invent a wheel, but for nature to develop wheels naturally, that would be almost unthinkable due to the specific challenges of how things evolve and develop. Anyway, so Dan Sheehan released a paper this fall. He had so basically, what common properties do all these sorts of systems? I'll get into the example systems shortly, but what common properties do these systems all have from experiment that have been found so far? Because that will direct where to look for new systems that can potentially do this. So Daniel Sheehan, in his experiments, has found 4 common properties of these systems. First, they involve asymmetries at boundaries. So, for example, surfaces of metals or surfaces between polymers, 2 different types of polymers, for example, or ceramics and metals, whatever else. So, and then the system in question has to interact strongly with the thermal reservoir. So, for example, I described this idea of biological systems. You have some interaction with polarons as a particle approaches a membrane, and that causes the protein to unfold in a certain way that grabs it's a receptor, essentially. It grabs onto something due to that interaction. So those interactions, even up to room temperature, can retain some amount of quantum character. And so you can have things that correlate to each other and then stick. So there's quantum behavior, and then maybe there's some classical examples, but I think mainly Daniel Sheehan and Vladislav Kepek's book talks about the quantum cases. So then there's this idea of orthogonal work extraction. So the way the energy is going into the system, for example, heat diffusion, is not correlated with the way the energy is getting used. So, for example, in the graphene energy harvester, you have your thermal reservoir, and phonons pass over a sheet of graphene, and that those phonons get captured as an electrostatic charge in a capacitor. Same sort of thing I mentioned earlier. That capacitor is unlikely to release energy back into the original system. And you can attach that capacitor to anything and it's not going to matter to the other system. I think that's what he means. Maybe he can speak more to that. That was slightly unclearly worded in his recent paper. But anyway, then there's this idea of a resettable metastable configuration. So for example, with the sewing machine model, you have your enzyme, and once these two particles that correspond to a salt or some other molecule that can come apart easily, once those two molecules are in place on the enzyme, they snap together again. And then the enzyme goes back to its original form. That's the sense in which metastable is meant there. So you have some system that once a condition is met, it harvests some energy, and then at the end, nothing has changed about that original system after the materials are released, for example. Let's see. Oh, and then I had a few insights as well. Generally speaking, these systems will have minimum operating temperatures that are dependent on some property of the system. So, for example, if you have a thermionic device, you have two plates of metal with one with a low work function, then the other has a high work function. And if you heat that up to a sufficiently high temperature, then eventually the Boltzmann distribution on the two metal surfaces, some population will become higher energy than the lower of the two work functions, and that will cause thermionic emission on one of the plates, but not necessarily on the other plate. So that allows this configuration with these two plates in vacuum to store energy. But you can't, the output will be negligible until the Boltzmann distribution has there's a sufficient population of electrons with sufficient energy to jump off from one plate to the other. And that is basically directly correlated to the work function of that particular material. So in some sense, you can think of some of these systems as having like a virtual heat sink instead of a physical one that has something to do with some property of your system. So, and a lot of these systems have potential energy stored in them. I'll explain, well, let's see, which example system? Yeah, the graphene energy harvester is a good example again. So in order for the graphene energy harvester to work, you have a flake of graphene between two capacitor plates, and it will wiggle up and down. And the energy, you don't get any energy out unless you have an electrostatic charge on the graphene already. And a lot of these systems also have potential energy. So for example, you could think of the thermal bath that the thermionic device I mentioned has. You can think of the high temperature as a potential energy threshold for the operation of the device as well. You could think of it that way. And yeah, these two realizations are related too. So this minimum operating temperature concept and then this potential energy concept are somewhat related for these devices. And also, one thing that may be the case, Daniel Sheehan mentioned that there's some asymmetry at boundaries. I suspect that also temporal boundaries are involved. So there was an old paper by, what was it, Friedrich Morgenthaler, where, I mean, he doesn't directly show this, but I show it in another paper somewhere. If you have an electromagnetic system where you change mu and epsilon, then that corresponds to changes in the wave speed V and the impedance gamma. And then that looks like this. So if you change your wave speed, your energy will go up or down. And if you change just your impedance, the energy will always go up. And there's a lot of nuance there. So you can have actually, it's not for sure that the energy will go. So this equation is not perfect on top, because in numerical simulations, what we found is if you've got two waves that cross on top of each other and then you change the impedance, you're changing their temporal derivatives, so you can actually cause them to cancel each other out. And the same sort of thing is true with, if you have one wave traveling, it can split into two due to reflections at the temporal boundary due to the change in impedance. So there's a lot of things that can happen, and usually you have an external energy source that you're causing the change in material properties with. But in principle, you could draw thermal energy from the material under certain circumstances, usually when you have a nonlinear hysteresis as well. So you have variable coefficient with nonlinear hysteresis. And in those sorts of systems, you're not changing or doing anything with your spatial boundaries. You're only modifying your temporal boundaries. So boundaries in a more broad sense than just spatial boundaries. But anyway, I can talk a little about the graphene energy harvester. So the reason why this works, or why this can work, is you've got your graphene flake between two capacitor plates, and thermal phonons come in from wherever the graphene is being held, and they go across the graphene. And the trick is the fluctuations on the graphene are not Boltzmann distributed, because thermal fluctuations in the lattice, if you choose, especially if you choose your material property, you could have like lead oxide or something, something that's relatively relatively soft and relatively dense. You want to basically minimize the size of your thermal phonons, but generally speaking, in most materials, they're comparable to the size of the crystal lattice. That's not necessarily true on graphene. On graphene, the speed of sound is extremely high, so your thermal phonons will get stretched, almost like it's like almost a magnifying lens. So all of these thermal phonons interacting with the edge of the graphene sheet, generally speaking, there will be a low population of them. And if there's a low population of thermal phonons, then you're not operating in the thermodynamic limit. And that's true for a lot of mesoscopic systems. So this graphene flake, for example, is generally meant to be about a micron across, maybe 10 at most. So because your population of phonons is very tiny, you don't get a Boltzmann distribution on the output, and that's why you can harvest that energy. And also you need something special called metal insulator metal diodes, which operate up to even optical frequencies in order to do that. And yeah, on the graphene flake as well, the other thing to notice is that thermodynamic temperature is not well defined. So same idea, if you have a bunch of particles going all in the same direction at once, that's the same as a very cold object, just with a very high kinetic energy, instead of like a hot gas. So the idea with the graphene sheet is that you also have a spatial dependence on temperature, where the interactions in the graphene sheet are very strong. So it's very stiff in one direction, and the interactions are very weak up across the sheet. So generally speaking, you're going to have up and down motions of these particles much more than left to right motions, especially with relatively low energy phonons. So your temperature is not well defined in two senses at least, and also with the proper diodes that operate at very high frequencies, you can rectify that thermal energy under those circumstances. So that's kind of the idea with the graphene energy harvester. And then you can take thermal energy, you put it in a capacitor, and then once there's enough energy stored up, discharge the capacitor as you wish and use that energy, and it thermalizes again. So other systems, Daniel Sheehan's talked about epicatalysis before. Generally speaking, that's where you've got so you have some molecule that can dissociate on one side and recombine on the other side, assuming sufficiently high environmental temperature. And then same idea for the thermionic device if you have a difference in work functions. Except in this case, you get a difference in temperature between the tungsten and the rhenium, and in the thermionic case, you get a voltage across there. So then there's the MIT 230% efficient LED, which supposedly that operates as a heat pump, essentially, which is fine. It can be 230% efficient as a heat pump. One thing I'm still curious to hear from them, which I haven't heard that info from them yet, but what's the actual output distribution? Because as long as the infrared output of their LED system is not more broad than the distribution of sunlight, then we have multi-junction solar cells that can capture 60% of that, and then you'd have an over-unity system. So it really depends with those 230% efficient LEDs. What data I would like to see still is what's the actual optical output of that device. And even if it is too broad, that's actually really useful, because if you can create an LED that produces an extremely broad spectrum due to thermal effects, then that's a lot better for plants and other things too. So, I mean, yeah, since LEDs are such narrow spectrum light sources, there's a lot of uses for broad spectrum light. So yeah, even if I'm wrong about the MIT LED being a possible route towards a system, that's still useful information to know. Anyway, so the membrane gradient cells, that's what we're working on now, Dan Sheehan and I. We've taken two different approaches. So if I can, yeah. So Dan Sheehan has a patterned membrane on the order of a micron thick. A similar idea, you got to get to a mesoscopic scale to get significant energy output from these things, because temperature is not necessarily well defined at that scale. But you have this layered material with sulfonic acid, for example, as functional groups on one side, and then carboxylic acid groups as functional groups on another thin layer of polymer. And because one side preferentially will attract the sodium ions, and maybe I have the pH gradient reversed here, but yeah, you'll get a slight pH gradient across a membrane like this. And this is relatively well known from experiments. But the effect is so small, you're talking about an ion concentration gradient of a factor of 2, and pH is a log scale. So for a pH difference of 1, you would need at least 4 layers of this, at least, if you get a factor of 2 out of it every single time. But you're not likely to get a full factor of 2 out of it once you scale that. It doesn't scale linearly when you add them. But anyway, the thing I'm working on is a little trickier. in some ways and maybe a little easier in other ways. So if you have quaternary ammonium ions on one side, and then you have sulfonic acid groups on the other side, then it's just like a diode. You have positive ionic functional groups on one side and negative ionic functional groups on the other. You'll form an extinction region between the two, just like in a diode. And that will prevent the flow of ionic, just ions in general. So in order to, you get a much steeper gradient in the concentration of functional groups. So that's potentially valuable, that's potentially useful, but you need to bridge that gap somehow so that the ions can still get through. And I use bismuth microparticles or bismuth telluride sulfide microparticles, which adsorb carboxylic acid groups very well. So I can use, for example, sodium acetate as a salt in the water, such that the ions of sodium acetate will separate on this system. And that's a little easier. I'm thinking roughly 10 microns across is reasonable for a system like this. And that, yeah, I mean, since the concentration gradient is easy to get sharp here between the two types of functional groups, I think this might lead to some interesting output, hopefully. But I'm in the process now of building that. I just made my bismuth microparticles yesterday, actually. And then to get electrical energy out of that, you can use manganese dioxide electrodes, because their electrode potential varies a lot with pH. So it's not super efficient, but you're talking about a similar technology to what was it called? Reverse dialysis is the thing. So you can get electricity out of a concentration gradient of any salt, but you can also get the same sort of concentration gradient electricity out of a difference in pH when you use this manganese dioxide. And I want to also try using cobalt tetroxide as well, because catalytically speaking, I think it should behave similarly. And also it doesn't get poisoned by carbon monoxide and stuff like that. But anyway, yeah, in a lot of these systems, like the graphene energy harvester was electrostatically charged. The MIT system was built up to some voltage that was not quite the threshold voltage for the diode. Other systems were heated up to a high temperature. In this case, the potential energy involved in these membrane systems relates to the fact that the ions want to recombine, but they're sterically hindered from recombining because they're attached to a polymer lattice that's holding them in place. So there's potential energy inherent in that. But that doesn't get used up when extracting energy from the system, because the thermal energy in the liquid is what comes out there. So yeah, so more controversial systems that I've heard of. There was this crystal power cell that I'm blanking on the name all of a sudden. Anyway, the crystal power cell, the idea is you have some combination of sugar and sodium bicarbonate and cream of tartar between two metals of different electronegativity. Now, I'm wondering with those systems, there's two things. So they were using gold on some of those and silver as well. Sugar can convert to glutamate on those substrates. So I don't know. And then sodium bicarbonate, I played around with trying to replicate the carb-pen cell long ago. And one of the things I tried was sodium bicarbonate, but I noticed that actually there was slow catalytic decomposition of the sodium bicarbonate, which produced a voltage actually. So, and we know that the sodium bicarbonate's decomposing in the crystal power cells, because some of those examples, eventually the central electrode gets pushed out and the salt mixture that they use increases in size. Which that just suggests to me that the sodium bicarbonate is releasing CO2 and decomposing. So those two things are not free energy. Those are energy sources that are built into the material that they're using. I would certainly like to see if they can use other glassy materials at the interface, because that might relate to the research with metal insulator, metal diodes. Usually the insulators in those are crystalline, but if you have an amorphous material in between, maybe that does something. So worth looking at. And then the other thing I wonder about is it really the electronegativity, or is it the work function? Because maybe there's some process by which electrons are jumping across the interface, and they're using this glassy material as a sort of virtual vacuum, instead of the thermionic devices that I mentioned before, where you have an actual vacuum gap. There's another material system that does this, supposedly, also controversial. They use a liquid with nanoparticles, and their claim is that these nanoparticles in this liquid, they have a work function as well. So you've made sort of a virtual vacuum state that's much closer in work function to the materials that you're working with on your electrodes. So instead of having this thing operate at 1,000 degrees Celsius, you have it operate at a couple degrees Celsius, around room temperature. And that's due to the close matching of the work functions of the material versus the virtual vacuum in between. And maybe if the crystal power cell is the real deal, maybe it has something to do with that and the work functions of the materials. Because generally speaking, highly electronegative materials tend to have lower work functions, or electropositive. No, I don't think so. Anyway, so then other things, those I also talked about just then. And then, okay, so another controversial system potentially, we've heard of a lot of systems that are that electromagnetic systems that cool themselves down and produce energy. These may be using parametric effects, like I mentioned, where you also have a nonlinear effect, a small nonlinear effect participating. So, for example, if you could make a LC tank circuit where you change your inductance and your capacitance slightly, then you can cause, in principle, Neal relaxation to become a driving term. So Neal relaxation in paramagnetic systems, and generally speaking, magnetic relaxation above the maximum remanent field. Both of those processes involve the thermal motions randomizing your magnetic field. So if you can get your LC circuit to resonate at that same frequency that the Neal relaxation is happening, which is temperature dependent also, so that complicates things. But if you can get the resonance to be matched, then the Neal relaxation will dump energy from thermal motion into your LC tank circuit. And then you can alter the inductance and the capacitance slightly. And then when you're putting energy back in, it doesn't take the same amount that that you got. So the parametric variation with a nonlinear process on top of it might do something. So, and that kind of relates to perhaps the most controversial claims of all. These would be first law violators, not second law necessarily. There's some claims that you have these Lenert equations, and generally, and even a larger set of electromagnetic equations called O3 electromagnetism by J.P. Vigure and others. And they claim that there's this thing called asymmetrical regauging, and they claim exponential growth and sometimes sudden quenching of the energy in these systems. But that looks a lot to me like what I saw when I was experimenting with parametric variation. And a lot of the asymmetrical regauging example systems seem to be parametric systems. So I don't know what to make of that. But yeah, you can have exponential growth and exponential decay just in parametric systems when you have these waves that either cancel each other out or multiply when they reflect when you modify impedance. And also, you don't necessarily get energy out of those systems if you modify impedance and wave speed together. You have to modify just impedance or just wave speed under certain circumstances in order to get energy out of those systems. And it's not guaranteed to come from the vacuum or from a material. That is material dependent and situation dependent on the system. So yeah, and also a lot of these examples claim to be entirely nonlinear systems, so not necessarily parametric or not necessarily with a variation of parameters. I mean, to know the difference, you'd need to know variational calculus pretty well. So that's, if you want to look into it, that's where to start, variational calculus. But generally speaking, if those systems are nonlinear systems only and they don't require parametric variation, then there's this idea of commensurability and self-oscillation. And for those sorts of systems, you still have your thermal motions, but when you're in certain regions of your parameter space, and there's usually an associated fractal pattern. I was hoping to have a picture here for examples, but I'll show that to Tim at some other later date. But the idea is under certain areas of your parameter space that are predicted by some fractal, you can have self-organization, kind of like how like hurricanes naturally form when there's heat from the sun going around the earth like that. There's or weather systems in general. And there's some chaotic variables there, but under specific circumstances, then you have a commensurable thing that forms due to the nonlinear dynamics. And those are called stable attractors. There's also chaotic attractors as well. Generally speaking, you're going to want to learn about attractor space and phase space and Liouville's equations. And that gets pretty complicated. And I can't say for sure at this moment whether that's also a second law violator or that their claims or that it's a first law violator. It's unclear to me whether they're just getting. So in order to break the first law of thermodynamics with an electromagnetic system, you would also have to break CPT symmetry. So that's another big thing. But anyway, for anyone, yeah, this is just for anyone who kind of wants to look into these things. These are things they should be aware of. Anyway, any questions?
Okay, that's a lot. Okay, so let me do this. Before we go to questions, everybody, Mr. Michael Perrone, a big applause, a big applause. And actually, that's a lot to do without a presentation outline too, because I know you're only halfway done. So thank you for running through all of that.
I mean, I had the words on the presentation here, so that was some of it, but no pictures yet, so it didn't really help. I mean, thankfully, I had many of the pictures literally just drawn out on paper while I was brainstorming. So, but yeah, I'm sorry I didn't get it all the way for this particular presentation, but we'll do it right on your channel at a later date, Tim.
Okay. Yeah, rock and roll, man. So let me see who has and if nobody has questions, we can go to open discussion one way or the other. Dun dun dun. Or maybe we should just do that. Do you guys want to just go to open discussion?
That's fine.
I
think
have a question.
I'm going to sleep. Oh, hey, cool.
Hey, Michael, when are you going to do a presentation on your Maxwell Demon device?
Oh, I have some of the stuff here. So let's see. I should have.
For those who aren't aware, Maxwell's Demon, of course, is converting thermal energy directly into electricity or
Yeah,
useful.
so where I'm at with that is, and I was hoping to show this more complete here as well, but oh well. So you've got this, oh. Yeah, so you have your anion membrane here, and you have your cation membrane here, and you stick them together. And you gotta, I made some bismuth sponge recently. And that'll crush up, and that should be like roughly average 5 microns in size based on my calculations. And you stick that between the two membranes, you wet the membranes with water, and they should mechanically attach to each other because their positive and negative functional groups will combine at the interface. And also, as an alternative to that, I have dispersions of ionomers in liquid, so I can paint them onto the surfaces if I need to. And I came up with this little clever, it's just a baking sheet really, but you've got these frames that are magnetically attached to the surface. So if I have to paint them onto there, or if I just have these two materials soaked in water, but they have different. So one of these things is, these are basically all gels in water. They have swelling coefficients. So when you put them in water, they'll increase in size slightly. And the amount that they increase in size by is different depending on the material. So these frames keep them flat to the surface as much as possible as they're drying. I don't know if I even want to make them dry fully, as long as they attach to each other nicely. So that's that. And there are 5 or 6 combinations of ionomers that work in terms of matching the swelling coefficients closely enough. So, yeah.
And this is for your device that uses a very a specialized double membrane to convert heat into a pH difference between the two sides of the membrane. And that pH difference is then able to be extracted as energy via electrolytic process, similar to a battery. So we're converting thermal energy first to a pH gradient using the membrane, and then from.
It's not electrolytic. It's more comparable to like a salinity gradient device. So if you've heard recently, many people are considering using rivers or the mouth of a river as an energy source, because as it goes into the ocean, there's a steep gradient in the salinity, and you can get electricity out of that. And they do that much the same way that I would with these, with the manganese dioxide in one case, but
difference is that the source of the energy in your case is direct thermal versus a river is just flowing in and you have all the rain process.
Well, I mean, technically it's indirectly thermal then, right? Because you have evaporation.
Indirect, yes. Well, at the end of the day, everything is solar powered.
Anyway, let's see. I do have some 3D models I could show, I suppose. Let me see if I can bring that up. And that will give more of a sense. I have to redo these a little bit because I talked with Dan Sheehan, and the membranes need to be much closer together to get more power out of the device. But if I can find it, just a moment. Is it there? Yeah, it's there. What was the thing again? Yeah, it's here. I've got this on Onshape if anyone wants to check it out later. I don't know how to. All right, share that. Let's see, almost. That's not what I wanted. Okay, there we go. Share screen. Share screen. That will do just fine. So yeah, this is the idea here, and of course it wants to invert that behavior. It's slower because I'm on the stream, I guess. But anyway, here's the idea. I've got some frames here that slot into this array here. And the frames will contain the bipolar membranes in my case. And you could do unipolar membranes with carboxylic acid and sulfonic acid as well, or different concentrations of functional groups as well. So you can have one that's got like double the functional groups of another. Generally speaking, that's harder because you'll have different swelling coefficients for different concentrations of ionic functional groups on the polymer backbone. So it's easier usually to go with carboxylic acid groups on one side, sulfonic acid groups on the other side. But anyway, you prepare your bipolar membranes. You cut 2 by 2 centimeter pieces. You stick these frames on them just so the edges are rigid, and you slot these into here. The plan is to seal the edges with just like silicone from Home Depot. And that I'm using sodium acetate anyway. So the solvent in the silicone is acetic acid, so it's not really going to contaminate much or anything. So you get about 12 of these in this. And in this particular device, I don't recombine them to make energy. I just have these 2 wells where you can stick a pH meter so that after a couple days, you can go see the pH difference yourself. And then you can remix the liquid and put it back in and see the pH gradient form again. And you can do that indefinitely until you're convinced that the energy density is beyond chemical for how long it's been doing that. And then the other one that I set up here, I also, called it a thermochondrion because it kind of looked like a mitochondrion when I was building it. That's not the one. There's a lid as well, so it doesn't get contaminants from the air or anything. So in this case, you've got the frames that slot in, and that's just still there because you can get rid of that. But anyway, you have your frames that slot in here. And in this particular setup, you have a larger frame on this side, which produces electricity from the pH gradient using the manganese dioxide that I mentioned before. So you just, for this side, which produces electricity, you don't have a selective membrane. You just have to limit the diffusion rate across the boundary between the manganese dioxide electrodes, and their electrode potential just varies a ton with pH anyway. So, and then you have just you have a small electrical resistance between the sides, but you limit the liquid diffusion enough that you get electricity out of that. And it's not super efficient, but it's good enough, and it'll show electrical power output from this thing in the steady state. Well, yeah, or it should. That's the hope. And the other thing, the thing I need to change.
Is that going to be like 3D printed at a PET-G or something like that?
Oh, I'm going to use ABS because then I can vapor polish it so it's watertight.
But PET-G is actually watertight without any modifications.
I did not know that, but so you just got to be careful. As long as your printer's good, you're fine. I'd like to take some extra precautions, I guess, because you never know if there's a small thing there. So yeah,
PET-G is what soda cans are made out of plastic soda bottles.
Right, but if your printer just like skips a little bit on the walls, you might have a hole somewhere that liquid could leak through, or you never know unless you vapor polish it. So anyway, that's the idea there. So I need to redesign slightly to get these membranes much closer together. Ideally, you want the whole stack of membranes to be like the size of one of these stacks of membranes. So I have to rethink some of that, but I mean, that's the general concept. It gets the idea across.
Okay, so let us go to Michael Boyd next. Michael?
Sure.
Hey, Mike. So
Hello.
I was thinking about this Maxwell's demon, and I thought of an example to understand the Maxwell's demon, and it is a little experiment you can do in your home. Is you find some dead batteries, alkaline batteries, and you take them and you put them in and you boil them, warm them up in water and you boil them. And then after you've done boiling them, you put them in a water bath with ice in it. And you let it reach temperature, and then you take it out and you dry it off, and the battery's like new. It's back to the 1.5 volts. And this is an example of a simple example of a Maxwell's demon. Essentially, you're taking
there's too many other things that are going on there. The challenge with proving, so you can do a lot of fun experiments, but the challenge with proving it for certain beyond a shadow of a doubt is you need to build this stuff in a very precise system that doesn't have too many side reactions chemically going on. For example, when I talked about the crystal power cell, you had your sodium bicarbonate and sugar, and it's known for certain that on noble metals, sugar will oxidize to glutamate, and sodium bicarbonate, even in ambient conditions, it will decompose as long as it's in water or has some exposure to water. So those, you need to make sure that you've removed any possible chemical reactions that could go on the side, and batteries are notoriously chemical-y, So it's in terms of clearly proving it out, that's the best way, because you don't necessarily know this or that manufacturer made the battery in this or that way. You'd have to go into all those details, and that's a whole can of worms. And maybe you can make your own battery and test it out. But then there's a whole bunch of other things too. So for example, if you boil a battery, you might not be changing much about, you might just be degrading any metal fingers that are reducing the efficiency of the battery. You might be basically,
well, when you heat it up, it makes it so that it's basically the most disorder, right?
Well, essentially it's electropolishing, but you're using the electrochemical potential in the battery already for the electropolishing, because you have some leakage current too. So you could be electropolishing the battery internals flat again, and then that would be a higher voltage pump, maybe. I mean, so there's so many things that could be going on with a battery. That's an interesting experiment, but I don't know what it proves. That's the thing.
I guess I want to chime in on this. I have 10 years of experience working with nickel metal hydrate batteries, and I kind of agree with Michael. Well, both of you are Michael Perrone on this, that there's a lot of variables with the battery. You can bring them back to life for a bit. I guess the real test would be to use one battery and do that process, Michael Boyd, do that process several times and count how many watt hours you're pulling out of the battery. And if you can continually do that, after a certain amount of time, there isn't that many watt hours in a AA battery. You must be getting it from somewhere else.
Well, I mean,
I agreed.
Something mechanically wrong with the battery that wouldn't work. But you can take 8, 9 batteries and you can measure them, and they'll be below the
I believe the voltage will change.
And do this process, and they all come back.
Actually, Michael, temperature is so important for battery output that we have a temperature controlled room over here for the battery lab that has a heater and a cooler, depending on the time of year. And depending on the temperature, you'll see a major increase or decrease in the battery's performance. Over here, we have high current tests.
Lead acid battery?
These are nickel metal hydrate batteries, but the same is true for almost all chemistries.
With a lead acid battery, you can buy this thing. It's called a desulfator. And what it does is
it's an overcharger. It's an overcharger.
It takes the sulfur condensate and that's how it's restored. And I had 4 12 volt, 255 amp hour batteries that I bought in 2002. And one of them, the one in the first one in the series, it lost the cell. But I still have those other 3 that were next in the line. They're all still good and performing like new, because you can restore those batteries. And you know, it's kind of unfortunate, because when people talk about solar panels and storage, they're always talking about lithium, which, you know, lithium, you can't, it's not renewable. It ends up in the landfill. It's not recycled. But lead acid batteries, 99.9% of them are recycled. So even though it's less efficient, in the long run, its life cycle impacts are much lower than lithium. I mean,
lithium batteries are recycled. They're not recycled maybe on a
1/10 of 1% of them are recycled.
the larger batteries are recycled a lot more now.
That's soon to change also. They're scaling that up a lot.
So, but my point is that there's this, when you're doing the desulfating, it's like you say, it's heating up, it gets hot. When I'm with my batteries, my charge control,
Michael, if you want to convert heat into electricity using a AA battery, you should do that several times and hook it up to a battery analyzer while discharging it after each run, counting the number of watt hours, specifically watt hours or joules, watt seconds, to know exactly how much energy you pulled out of it.
How much? I didn't know it had even a watt. What kind of watt hours does a AA battery have?
A AA battery probably has several watt hours.
Really?
Yeah.
Okay, well, I learned something.
Maybe probably less than 10, but you could measure it in joules then. A joule is a watt second.
So a 250 amp hour battery would have 12 volts times 250 amps. That would be the watt hours, correct?
No, amps is not. You need the amps times the voltage. You need a battery analyzer to get that measurement.
It's rated at amp hours. Amp hours.
That's how they sell it. That's how they sell it to you, but that's not a very useful piece of information. Because if the voltage drops down a lot, then your watts drop down. Really, what you need is the watt seconds, the joules.
How many days of power do I have if the power goes out? That's all I care about.
Oh, we're talking about Maxwell's Demon. If you can get thermal energy conversion using a AA battery by putting it into a bath of hot water, and you're actually converting energy from the bath into electricity on the battery terminal, that will be very interesting. But you need a battery analyzer, and you have to count how many joules you're pulling out of the battery, and then repeat it many times and see how much you're actually getting out of the battery, and then do the same experiment with a new battery of the same type.
You have to cool it down. So what you're suggesting is I could go buy like a new battery, discharge it, do the same experiment, and then do it with a dead battery, and compare the two and see what the performance of it is, correct?
Yeah, but you need a battery analyzer to really check performance properly, like a West Mountain computerized battery analyzer. That will work.
Okay.
Try to keep the current pretty low, and you want to leave it like at 100 milliamps, a tenth of an amp at most for a single AA.
Okay.
Just run all your experiments on one AA. That's all you need.
Okay.
Well, if it's okay, why don't we go to how CC?
What was that? Westmont? Say the name again of the analyzer.
West Mountain CBA.
And then we can do the battery analyzer thing, that we can kind of come back to that in open discussion, because
Okay, thank you.
yeah,
Michael might need that as well if he wants to figure out how much energy is coming out of the system. A West Mountain CBA, that'll give you milliamps or amps of discharge. Tell you how much current you're pulling out of it.
yeah. So
I've got a Keithley DMM 6500. It can measure like nanoamps or something.
okay,
Oh, okay.
so let's go to How CC. How again, and then after that we'll do open discussion.
Yeah, regarding what you said, Michael, about halfway through your discussion, I think you were talking about the contrast between, say, a log or wheel appearing in nature and what we find in the cellular phenomena. Would you ascribe that the first question would be that from the standpoint of having a heat reservoir in the microscopic world of chemical reactions, you would expect there to be very small energy drops in the cellular arena, which nature had to do because organisms had to find a way to conserve their energy that they were chasing down to thrive. In other words, an animal would have to eat, and it, depending upon when it would catch its prey, it would have to be very conservative with its energy. So nature tended to go to a very small step scale way of extracting and holding onto what it had acquired in, say, hunting. You see what I'm saying? Whereas,
All right.
yes, and in the case of a wheel, which is a man-made object, the objective was to get very high power densities out in a very short period of time. So you had one which was a scale of being very conservative with a very parsimonious type of energy situation, animal eating and being able to wait for its next meal, versus a man-made object which had to do useful work in a very short period of time, like a car engine would burn fuel to get a high degree of energy out. So I guess, go ahead.
So the reason that a wheel, for example, is not a likely thing to evolve in nature is because you would need, first off, you need there's some attractor space corresponding to the growth pattern of an animal. There's some stable, well, usually it's a chaotic attractor that describes the growth and homeostasis of an organism. And that attractor needs to deform continuously. It can't deform, it can't, so yeah, so basically to evolve a wheel, that wheel would have to be a separate piece than the organism, otherwise how would it be attached? So you haven't deformed your attractor space, or you haven't deformed your attractor corresponding to the homeostasis of the organism continuously in order to develop that. And in the case of, well, yeah, in general in evolution, there are a lot of things that are in principle that nothing violates the laws of physics, and things that we, like humans, have invented them, but it would be very unlikely for nature to discover them because the difficulty of that evolutionary jump would be so high, like the case of the wheel. And with thermal harvesting, thermal energy harvesting, there's two things to consider. Maybe we do have it to some extent. Maybe some of the enzymes in the human body, some of the energy that those enzymes use, it comes from ambient thermal heat. And that optimizes them for some process further than they would otherwise be able to go. So it's unclear whether or not it hasn't evolved necessarily, but it certainly isn't the main energy source for living organisms, because there are much larger energy sources readily available. Maybe on a planet that didn't have direct access to the sun, but still had enough thermal heat, organisms would eventually figure that one out. And those would be the ones to grow. Maybe on Europa, for example, although there would still be chemical gradients, that might be more energy dense than thermal gradients or thermal sources. And then the other thing to consider is if you're going to build a protein or enzyme that can harvest heat, how much energy and resources does it take to make that protein? And it's not usually enzymes and proteins and things eventually break down. So how long is it going to last? What's its half-life in the body? And are you getting more energy out of it than it took to make it? And you may have situations where you do get more energy out than it took to make it, but it's not enough to really matter. It's the same idea with like oil these days. It's taking more barrels of oil to produce each new barrel of oil. And even though we're still getting out more barrels of oil than we're putting in, and that runs the whole modern economy, it's getting a little bit sketchy in some places in terms of the cost of energy. And I mean, that will continue as we run out of oil, and eventually you won't be able to get a free, like more than you put in out of that. So it's unclear which side of that the like thermotrophic, I guess, cells or organisms would be, but it's possible at higher temperatures especially that it's a feasible way. And then maybe somewhere deep in the earth, organisms like this do exist. So yeah, I mean, just some stuff to think about. Yeah.
Another thing that I wanted to kind of just, and I'm not making a complete thought here because I'm not deeply familiar with it, but kind of the marvel of the kidney. You have a blood flowing through the kidney, and on the other side, there's no really, I guess in one sense, there's nothing there. Urine is produced, but I assume it's not continuous. And the point I'm trying to get to is that you have a kind of an osmotic system in which you have something which is from a high gradient, a solute flowing to a non concentration, a zero concentration on the other side. And I was thinking that if there was a way to find a way to reverse that so that we could take salty water and without the high pressure to drive the osmosis, from the highest salty to the freshwater side. If there was a way to reverse the engineering of the kidney, we might be able to get to some degree of free production of fresh water without necessarily the high pressure. Has there been any thinking on that? I don't violate the thermodynamics. I just think there'd be a way to engineer it. It's sort of reverse kidney.
Yeah. So that's called reverse electrodialysis, and they're using that to make power stations at the mouths of rivers. So reverse electrodialysis or reverse osmosis. Yeah, it's usually called reverse electrodialysis the other way around, which would just be kind of osmosis, but you have electrical output. But anyway, yeah, they have these systems. They are considering using them for power extraction at the mouths of rivers. It's a thing that people have considered in the past, and there's other ways too. You don't have to go directly to electrical energy. You can simply use direct osmosis to make a water column that's way above the sea level, and then you just use a usual hydroelectric turbine. So you just the osmotic pressure makes a water column, and from that water column you just get gravitational energy into a turbine. So there's tons of ways to do that. But yeah, in the kidney, that's interesting. That's an interesting thought, because maybe there are some processes. I know the nephrons in the kidney have many active ATP driven processes in order to sort all of those molecules, but perhaps a few of those sorting processes are second law violators. That would be an interesting place to look.
Yeah, I just was thinking that might come about in trying to kind of get the gist of what you were saying. It struck me that there might be some processes, like I was saying, in the kidney that just supported what you just said, that there might be a way to utilize that in advantage for separation of water, since water is so critical. Another question I have quickly is, to summarize what you were saying, I listened to your whole talk, but are you basically searching for a way to get energy out of these chemical systems in small quantities to harvest, or what is your objective there of what you say?
So I was hoping to have my presentation fully ready. The idea was to make a general overview of all of the most promising second law violators and the general theory behind them that's being developed. I didn't have all my pictures in my presentation, so I just kind of winged it. But yeah, generally speaking, there's various fields that you need to be aware of if you want to go trying to test these things, various concepts. So, I mean, like Louisville's equations for one, Poincare cycles, and then there's a lot of basically the biggest area of uncertainty in thermodynamics is really with the axioms that are chosen and where those can actually be applied in real physics. So that's really things to be aware of when hunting for potential second law violators. Are like, where do our thermodynamic principles actually apply, and what parts of thermodynamics can we still use, given that the assumptions are not true, and what are the general behaviors that have been observed about all of these systems that match up. Yeah, so that's the kind of, yeah, just kind of pointing the way, I guess.
Okay. So I think we're coming up on why don't we go to open discussion then? And so everyone, thank you. Let's do this. Let's give Michael an enormous hand. Sir, again, without having kind of an organized presentation, you're doing awesome. So